going to talk today about just how we assess uncertainty in our models when thinking about predictive accuracy. And at the end, I'll talk about an application in chronic myeloid leukemia. So just an overview is that more and more, I think, mechanistic and sometimes we use the term quantitative systems pharmacology models are used in guiding drug development, and even the FDA is seeing them more and more often. And a complicating factor is that just these models can be extremely complex and have a lot of assumptions, and they can be hard for someone who didn't work on the model to assess and understand. And so we've been thinking about how these models can be validated in a more structured way. And in this talk, I'm going to talk about two approaches. One is around just developing simple heuristics when it is possible as a benchmark. And another is this like an uncertainty pedigree table that we've developed. And so for the overview for the talk, I'm going to start just with mentioning some of the challenges in building predictive models. And then for the simple heuristic tool, I'll just show two examples, one in weather forecasting and another for cardiotoxicity. And then for developing a credibility assessment and pedigree table, I'll talk about some modeling work in CML. And I thought here, just because people have different definitions of what a QSP model even is, and so I just thought I'd throw something up here. I know there is no like established definition, but I try to kind of distinguish between, the more mechanistic PKPD models where they might be like a relatively simple model and you understand something about the mechanism in the model. So it can give you insight, but it's also you have a chance of getting mathematical insights and aspects of the model being identifiable. Where sometimes the more systems models, can be much bigger, and they can still give you a lot of mechanistic insight, but they can just be more challenging to analyze. And so first, I'm just going to start by talking about a few of the challenges. I mean, like a big one is just this reproducibility crisis that you see where, there's even like in the last few years, there's been, many efforts to try to reproduce, papers from Nature and Science. And this bar chart here just kind of summarizes various references. And the non-reproducible studies often outnumber the reproducible ones. Some of the possible reasons it could happen, I mean, sometimes you have cell line misidentification where you think you're working with one cell line and it's actually another, or sometimes you're using antibodies used for a protein with poor specificity. And sometimes there's just so many features of an experimental design, it's hard to elucidate them all. And when you build these mechanistic models, I mean, you're relying on data from the literature often to inform them. And so this is kind of just one of the challenges. Another analogy we often make is that, in physics and engineering, like mathematical models have been, like a godsend for helping us, here I'm just showing some like fluid dynamic models and the like Navier-Stokes has been around like a long time, and it's you can put these equations in the computer and they're, relatively well understood. Whereas like on the biology side, I think one of the challenges is our knowledge of biology is always changing every year. They're always finding new things. When I put this talk together, I just searched for the term like biology and then rewrite the textbooks to see what came up. And, here was a case of them discovering lymphatics in the brain, or here, like in studying diabetes, and trying to understand the immune system's role. Everybody knows about B cells and T cells. But then there are these DE cells that express both the B cell receptor and T cell receptor. And, with things like the immune system, they're so complex with so many, cytokines being simultaneously like inflammatory and anti-inflammatory that, as our knowledge changes and evolves, the predictions of our models will change and evolve too. And the last challenge is around structural model uncertainty, at least the last challenge I was going to mention here. So I think like the butterfly effect is something that like, most people are familiar with from Jurassic Park or other things where it's just, a small change in the initial condition or a small change in your model parameters can lead to large changes in predictions. And this is an issue, I think, to some extent we know how to deal with it well, and that you can do sensitivity analyses or simulate virtual patients and explore like a large range of that parameter space to just understand the consequences of that. But the butterfly effect has this ugly cousin known as the hawkmoth effect. And that's where also small changes in the underlying structural model can also give large changes in the prediction. And the challenge is really, how do you systematically explore, all the different structural models that might give behavior consistent with some of the data you've collected. And that's a lot harder. I mean, I think the short answer is you can't. And so it just kind of requires a lot of thought and collaboration, and it's just sort of a challenging thing to do well.
Andy, could I ask a brief question about
Sure.
you? Sorry, yeah, you mentioned the reproducibility, or this sort of domain's version of the reproducibility crisis. Is your focus, so that I understand where you're coming from, on the making sure that studies can be reproduced, or the fact that many attempts at reproduction fail to replicate the original results?
I see. I mean, honestly, both are important, right? I mean, I guess. I think I would just say both are important. I know in different fields there are like big efforts towards, making sure data is publicly available, or code is, or, making sure, as much detail is provided as possible. I mean, I think that's one of the core things. But yeah, I guess I was just here. I think I'm just trying to give a high level overview of some of the issues. I wouldn't myself think propose how to solve it even. I think that's maybe even beyond the scope of what I came to talk about. I think my focus is more given that this is a concern, how to think about it when it comes to building our models based on this data.
Sure, that's fine. That's fine. In case there was a very specific focus, I wanted to make sure I wasn't missing it. Thank you.
Sure. Are there any other questions? Okay, yeah, feel free to chime in with questions during the talk, and I'm happy to answer. Yeah, so here I was just talking about, there's these two tools when it comes to thinking about parameter uncertainty that we have for dealing with it, which is global sensitivity analyses, where you vary the parameters over a range and try to understand the model sensitivity, or just simulating a cohort of patients from this distribution. And a lot, especially in the QSP literature, I think a lot of focus goes on to those two things. But for something like structural model uncertainty, that's often not even discussed very much. And a little bit, I think what's going on is something called the streetlight effect. So the idea here is you have this poor guy in midnight searching for his keys, and he can't find them. And a police officer comes by to help, and he asks, is this where you lost your keys? And he says, no, but this is where the light is. So this is where I'm looking. And I think, when it comes to model assessment and thinking about if we're confident in our model predictions, we know how to do these things, like sensitivity analysis and at least simulating patients from our model. But there's this whole other set of things that are more in the dark that are, can be harder to think about, like the quality of the experimental data, like how well do we even understand the biology? Do we even understand it well enough to build a model for making predictions that are going to guide decisions? And so in this talk, I'm trying to kind of shine a light on the right-hand side and offer a couple tools for what to do when these sources of uncertainty are kind of significant for our models. And I first want to just talk about the using simple heuristics approach. And I'm going to put it in the context of the bias variance trade-off. I mean, this comes up in machine learning and stuff all the time too, when you're thinking about how complex to build your model. And so there's two key factors that can lead to a model error. I mean, one is bias. And so if your model has strong assumptions, or if it's too simple and it's just incapable of describing the data you have, then, one source of error, on the left-hand side here, when you have a model that's too simple, is you can have a lot of bias. And then on the other side, there's the variance, where if a model has too much flexibility that it can describe anything, then you can often like overfit noise in the data. And noise could be, an experiment that was, maybe run under conditions that weren't totally understood, and so you're kind of fitting data that, doesn't represent your model of the reality. And so variance becomes more a problem as the models get more and more complex. And so when you add up the two sources of error, you get this parabolic shape, and the hope is, you want to be in this kind of sweet spot in the middle. It's sort of like a parsimonious model. And so, whenever you build any model, you're going to be somewhere on this curve, and you're not necessarily going to know where you are with just like one point. And so the idea is, so let's say you build your QSP model to have like a benchmark you compare it to. So if you have a simple heuristic for making predictions and your QSP model is like outperforming that, then that's like a really good sign that it's giving you insight beyond what you had going in. But in other cases, it's possible sometimes that like a simple heuristics like outperform the QSP model. And in that case, the model, maybe it's like overfitting some variability in the data. And so having this heuristic is just a way to kind of like benchmark your model. And I want to show two examples. I think I'm going to start with one from weather forecasting, just because that's such a data-rich area. And here's a slide from Dean Bettino and Pete Bonate about just showing like the comparison between weather forecasting and say patient forecasting on the right, where you start with like lots of data from lots of different sources. And then with weather, say you're trying to predict where a hurricane's going to go, and then you're making a decision about if you're going to stay put or evacuate. And then for a patient, you're making a prediction about how a disease is going to evolve, and then should you stay on your current therapy or change therapies. And then the specific weather forecasting example I want to talk about is just around temperature forecasting. And it comes from Nate Silver's book on the signal and the noise. And there's two kind of big approaches for predicting temperature. One is we can build a computational model, right? So you take all the data that's collected and then all our knowledge from atmospheric sciences, and you try to put as much as you can into a model. But of course, there's also features you can't describe, like describing the evolution of cloud cover, right? I've heard is like really challenging. And then all the way on the other extreme, there's this really simple heuristic you can do where you have the last 100 years of historic temperature averages, like, every day. So if you want to predict the temperature one day in the future, you just look at the average and take that. And this takes none of the knowledge of today, like atmosphere, into account, but it's a really easy to implement and understand method. And so when you compare these two approaches, so it's shown here in the x-axis is just the days in advance you want to make the prediction. And then the y-axis is the error. So like lower is better. So when you're trying to predict, less than a week in advance, the computational model does the best. But as you predict farther and further out into the future, the data that inform the model becomes like less and less useful, and noise and errors can propagate throughout the model. And then more than 10 days in advance, so you're better off just using the historical data. And for me, that's really, I think it's been like a useful lesson just to think about, is that, and for any particular application, we might be on the left side where like a computational model is really going to provide a lot of insight, or we might be on the right side where, simple heuristics might do better. And it's really hard to know where you are unless you do the comparison. So here's just like one example where like a colleague, Hitesh Mistry, has done something where the goal here is for predicting cardiotoxicity from ion channel data. So, with all drugs, like small molecules anyway, if they like affect the hERG channel or other ion channels, there's a chance that they could alter your heart rhythm and lead to torsades de pointes. And so people do these in vitro ion channel assays where they'll give the drug and they'll look at, how do these drugs affect the different ion channels and affect repolarization or depolarization. And, like one approach you can take, including like the FDA has done this, they've kind of built a computational model of the cell and all the different ion channels and try to, really build a model of all that data to and then they make predictions about how, the cells will be affected. And, an alternative approach that Hitesh developed is just, the simple heuristic where, you take the drug concentration you're interested in, and then you add up all of the, at the concentration of interest, how much repolarization is occurring on the different ion channels. You add that all up, and then you say how much depolarization is happening, and you subtract that, and and this is it. Like, this is just a simple heuristic, right? So it's ignoring a lot of the complexity here, but it is, somehow taking into account the, what's happening. And so what was done was they compared the different approaches with a few different, these were like 4 different data sets, either using 3 ion channels or 7 ion channels. There's a simple approach using just the hERG ion channel. Then there were the 2 kind of mechanistic modeling approaches here. And then the BNet, kind of the simple heuristic I showed before. And what's shown on the y-axis here is the predictive accuracy measured by like the receiver operating characteristics. And so you see here is that, this actually, the simple heuristic really, did as good or a better job than the more mechanistic models. And so, that's not to say that, the mechanistic models can still give a lot of insight, but it could be a lot of the predictive power, from these mechanistic models just comes from understanding, the balance of repolarization and depolarization. And I mentioned here, a few other domains where simple approaches can be used. So, like for us, a key thing we may have to predict is like a first in human dose that we think will be safe, but possibly still active. And so you want to predict the drug concentration in humans. And, you can build like a full PBPK, mechanistic model, but there's also some kind of simpler techniques for making those predictions. Like another area too is this, when there's a lot of interest in drug combinations in oncology and trying to predict, when can you really put 2 drugs together and get something synergistic or something, beyond what you might expect. And so there's like a lot of groups that have built kind of some detailed like quantitative systems pharmacology models for that. But there's also a simple approach, just assuming independence of action that, because there's so much heterogeneity in the population and so many different sources of resistance, that you could just think of each drug gives you a chance of responding. And if you take 2 together, you get 2 chances. And that's not to say that this approach is always right. Like you'd hope if you understand the biology well enough that the mechanistic model would work better. And it's kind of the idea of like doing the benchmark as a way to get a sense of where you are. So I think, these simple heuristics are great when you have problems like this, that are kind of reproducible, right? Like you can find data sets maybe where you have like dozens of predictions you're trying to make, and these kinds of predictions have happened like hundreds or thousands of times. But like often we're developing a new drug for a new target, and it doesn't make sense to talk about like looking at our predictive accuracy over like 50 scenarios. We only have like 1 scenario we care about. And this has a lot in common with things like predicting the economy or climate change or things like that, where we only have 1 Earth, right? And so there are these context of use tables that the FDA developed, and then also an uncertainty pedigree table that I'm going to talk a bit about. I just mentioned here a couple of references I referred to. This first paper was a white paper the FDA put out a couple of years ago. And the focus there from the FDA paper was just on the context of use. And so it's just on getting a lot of clarity on like what exactly the model's being used for. So really getting clarity first just on the question and the methods and data being used. And this, I think we probably all do this, at the beginning. And I think it's like the next part I think I've learned recently is more and more important to think about is first, when you're trying to inform a decision about, say, the design of your clinical trial or what dose you'll test, to just think about, how important is the model relative to all the other evidence that's going to go into making that decision, and whether or not the decision would change without the model. Because honestly, if the decision wouldn't change, that it could still be a useful learning exercise to build the model, but it doesn't mean you have to like validate it at the most stringent level. Another question is like, what is the risk that the model's wrong? And then if the model is wrong, oh shoot, sorry for that. If the model is wrong, like what are the consequences? So if there's potentially like really bad consequences for the patient, like maybe giving them a dose of a drug that's too high, then you could say you want really stringent validation criteria. But if you're just using the model to guide your next preclinical experiment, and you have room, the consequences of being wrong maybe aren't huge. And so then maybe like a high degree of validation isn't needed. But once you have that idea, then the next step is to come up with a validation plan. And there we've tried to learn a lot from folks that have really, like these folks down here spend a lot of time thinking about uncertainty more for things like climate change or health impacts or like, environmental issues. And what they do is you come up with they call it a pedigree table, where you like identify like all the different potential sources of uncertainty. And then you ultimately give each kind of a qualitative score. And so here's just like an overview of some, right? So there was like experimental data is one that we talked about before. And to what extent, are you dealing with like validated assays from, highly, validated labs that are strongly trusted, or are you going from papers from 50 years ago? Another is there consensus in the community on the underlying biology, or is it really still an embryonic field where we're still learning? For structural models, right? Did you just kind of try to come up with one model that was consistent with your data? Or did you really try to, think carefully about the assumptions and consider a lot of different models that might also have been consistent with the data? There's standard techniques for thinking about how well does the model describe the data, and that's helpful for assessing interpolation. For extrapolation, I think what can give you a lot of confidence, right, is if your model has been used to make a lot of surprising predictions, and that might give you confidence in making additional predictions then. And then the next thing is around thinking about inter-subject variability, when we're in the clinic, and people will always try to simulate it, right? But I think the question is, do we really understand the source of it and how, the different factors might all be correlated with each other? Or are we just kind of making some general guesses for where the variability would go? And if we are making guesses, just thinking through what the consequences of that. I talked about parameter sensitivity before, either like local or global sensitivity analysis. And then the last thing is just quality control that I know, like in every model I've ever built, if it's an important enough task that someone's come along to validate it, they've always found some mistake that I've made, even if it's simple. And so like, is that extra level of quality of control in there? These are all things just to consider how, each of these can be given a score. And depending on, let me just skip ahead, depending on the type of thing you're using the model for, you might like require different scores. So what I'm kind of showing here is just different scenarios, right? So in one scenario, if you're just using the model to like explore hypotheses about a pathway to help motivate new experiments or new targets to go after, you might be able to tolerate like relatively low scores. You might not even care that much about patient variability. But if you really, I think the hope is like long-term is these mechanistic models, maybe they can inform a change in label or, a change in a late phase study design. And so in that case, you really want much stronger validation criteria. One thing I would say too is, because these scores are qualitative, they're also kind of arbitrary. And so you could imagine different people have different perspectives, and it can actually be a useful conversation tool, like a way to kind of structure conversations around a team around some of these different features. Let's see. Yeah, so, and I think with these tables, the one I presented was at a very high level, but they say, you can always go even parameter by parameter or detail by detail if it, if the application is important enough. And so that was kind of like an abstract discussion, but I kind of now wanted to show what happens when we look at Gleevec therapy in CML. And this is going to be a retrospective example, just to show how but I think it's it's just a useful, I think, thing to look at how it would play out retrospectively. So just get an idea of like what, ways it might be useful going forward. So probably everybody knows this, but I just wanted to go through really quickly that, in CML, the causes is you have a translocation between these two chromosomes. And at the point where they're translocated, the gene for BCR and the gene for ABL are put smack dab next to each other, and you get this chimeric protein that no healthy cell makes. And with BCR-ABL, it's a constitutively active kinase that triggers proliferation. And so Gleevec comes in and it inhibits the phosphorylation. And so it, it leads to the death of like leukemic cells. And the reason I just wanted to go through with BCR-ABL that little bit is because this is their main measure of the disease. And so this on the y-axis here is the percentage of BCR-ABL transcripts in the blood relative to ABL. And what's great about this compared to a lot of other cancers is because no healthy cell can make it, you can get really, really sensitive levels of detection, like down to 0.01% here. And what you see, this is just a summary of like the IRIS study. This is like the first big clinical trial for Gleevec. You see this biphasic decline, where you have first a rapid decline in the transcripts and then a more gradual decline. And the rapid speed happens over about 12 days, but then the more gradual speed is over like a year. And I think whenever you see something on like a logarithmic scale and you see these slopes like this, that gives you a chance that there's some physical processes, right, we'll be able to describe. One thing I wanted to say quickly is, this is an overview of the population, and most patients do have this kind of classic biphasic response. But there are, sorry about that. There are some patients that don't respond at all. They'll have like a primary resistance. And other patients that start out biphasic, but then they have, they have resistance that can be observed maybe like 3 years out. So the focus here is really going to be on understanding the biphasic response. And the really question is, can we like look at this data and make a prediction about what's happening with the stem cells, the leukemic stem cells? Because there's a question around, Gleevec is a great drug and it's relatively safe, but, patients are taking it for the rest of their life. And people want to know, is it possible to discontinue therapy safely? And so here's just the history of it. So Gleevec was approved about like 20 years ago. And in 2005, the first Gleevec modeling paper came out in Nature. And it predicted that Gleevec did not impact stem cells at all. But then a year later, another modeling paper came out in Nature Medicine, and they predicted that Gleevec did impact stem cells. And so year after that, that's when the investigators initiated the first discontinuation study. And the initial results from that study was around 40% of the patients maintained response after discontinuation, and the rest relapsed quickly and had to go back on therapy. And these numbers are still around 40, 50%. I mean, that's still the way it is today. So that you can discontinue, but it's like strongly recommended that you're followed frequently to make sure that there is no relapse. And then a little later, we did some work trying to understand what happened here between these different models and looking for additional evidence, just from the data itself that Gleevec would impact the stem cells. I think the fact that you saw, patients discontinuing and maintaining response means something must be happening. And so I'll present some of the evidence here. So just to start with the context of use table, right? Our question is, can the patients discontinue? And, we're gonna show some mathematical models fit to the data. In this particular case, the model influence was actually none. As far as I know, the investigators just ran their study. Even though they worked with the modelers, I think they were just, as best I can tell, they think that, at least back at the time, thought the models were interesting ways of looking at the data, but were kind of not necessarily driving their decisions. And because they were carefully monitoring the patients in the study, if the disease started to come back, they could have the patients go right on therapy. And And so in this case, you could think, since the model didn't impact a decision, it was okay, maybe strong levels of validation weren't necessarily needed. But if you did want it, I think it's a useful thought experiment to think about if you wanted these models to inform the decision, like what you would do. So here's just sort of the overall kind of structural model for describing hematopoiesis. So you start with, in the tens of thousands of leukemic stem cells in your bone marrow. And then through like 30 generations of proliferation and expansion, you ultimately get to, trillions of cells in the bone marrow and hundreds of billions of white blood cells that are, produced every day. And so it's captured, in just 4 to 5 compartments shown down here. So there's the stem cells, the early progenitors, late progenitors, and then ultimately the white blood cells you see in the blood. And the first model that was developed was like the MECOR model in 2005. And so it started with the healthy cells where, you have expansion all the way to the white blood cells. And then the leukemic cells can expand a bit faster. And then when you give Gleevec, you have like the late progenitors decline at a rate alpha and the early progenitors decline at a rate beta. And you can also have resistant cells that don't respond to therapy, but are maybe present at much smaller levels. And then to take this model and link it to the data, we have like a measurement model here, where each of these cell types can produce white blood cells. The healthy cells would produce 2 ABL transcripts per cell. And then the leukemic cells would produce 1 ABL transcript and 1 BCR-ABL transcript. And then our measurement assay is the PCR with the ratio of BCR-ABL to ABL. And so you're taking the sum of all the BCR-ABL transcripts. So you have 1 from the leukemic cells L and 1 from the resistant leukemic cells R. And then you have all the ABL transcripts down here. So you have 2 from the healthy cells and then 1 from each of the leukemic populations. And what was seen was like the model did a great job describing the data. So here's just 6 individual patients, and it's seen, yeah, they all there's 5 individual patients and then a summary. And you see, you see this biphasic trend, and the model 2 predicted a rapid relapse because there was no effect on the stem cells. And then these 3 patients that were followed for like 1 to 3 years on therapy, the model also predicted a relapse. And so it described the data well. And so if we think of this in terms of the pedigree table, that the data, I'd say that went into this was like very good. I mean, the assays are run by like excellent, some of the best labs in the world for measuring BCR-ABL. But that this was still like early days, right? So there's not necessarily even though there is a consensus on the hematopoietic process, the way that Gleevec acts was not yet well established. And really only one structural model was explored in the paper, like not other options or assumptions weren't considered. And so, right, they started out assuming Gleevec didn't impact stem cells. And so, of course they saw everybody relapse quickly, but other possibilities weren't really considered. And so then like the next year, this is the second paper that came along from Ingo Roeder and others in Germany. And, they used an agent-based model here, like modeling a whole bunch of individual cells cycling between an active phase or a quiescent phase. And then you'd have these proliferating precursors, and then eventually cells would wind up in the blood. So here I just show it in terms of, you could represent, when you have enough cells here, you could represent it as a compartmental model, at least when there's large numbers. And again, you can have these like 3 arms like before, but the difference now is the Gleevec affects, it affects all the proliferating cells in their model, and they decline at a rate alpha, and it's a rate beta at which the quiescent cells become active. And they use the same measurement model I described before. And again, their model also is consistent with the data. It has this nice like bi-exponential trend. And again, if you do the pedigree assessment, I mean, this is just kind of the same story again, right? And that the data, again, the lab, this was a different lab they were getting the data from, but it was, another one of the best labs in the world. But again, only one model was considered in the paper. And here they made the assumption that Gleevec did impact stem cells without exploring other hypotheses. so later we considered, in a paper we worked on, there's actually, and if you make the space of models bigger that you consider, you can kind of put all these different hypotheses into a single framework, right? So you could have Gleevec affecting the latent early progenitor cells, giving the alpha and beta slope. You could have it affecting the early progenitor cells and then the leukemic stem cells, and that's your alpha and beta slope. Or you can go all the way to the rotor hypothesis where, alpha is the leukemic cell death, and then beta is the rate at which your quiescent cells activate. And eventually there was some data that's shown here where they actually went in and they looked at the different cell surface markers in the bone marrow to identify the different types of cells, and saw that like all types of cells that they could measure in the bone marrow declined at a rate alpha. And so it was like this kind of data that was really needed to help choose between the different models. So this first model I showed with the, where the leukemic cells aren't affected at all, it would predict that they keep growing, which isn't what's observed. So we know that that model is wrong. And even the second model too, it predicted that the proliferating stem cells only decline at a rate beta. And that's also not consistent with what's seen in the data. So the only model that's consistent with the data was this one here, where Gleevec's basically killing all the cells that are proliferating, and it's only the quiescent cells that need to wake up in order to be killed by the disease, and those are what contribute to the long-term decline. And so if we kind of do an assessment of that, there's additional evidence now that, for what's going on based on, having the data from the bone marrow. And so we consider 3 structural models, right? But there's still like other processes that are left out, right? Like we didn't consider feedback, or we didn't consider the immune system interaction with the, with the disease. So, depending on the question of interest, it's possible this approach or this, these models aren't even good enough. One thing I wanted to say that, I think I was maybe like in this talk kind of like critical of this work, but I think it was really valuable and like really useful even to have the insight to take that data and try to model it. I think the fact that they didn't, a decision wasn't based on a single model is fine. And so, but it's just, if you really are going to use it to guide a decision, that's where you might want to do kind of further validation of it. I think one of the ways I just wanted to highlight that these models were useful is just recently, like a new BCR-ABL inhibitor was approved, and actually the dose regimen that was approved and on the label is different than the ones that were tested in the phase 3 studies. I think there was some evidence that taking it once a day could be safer and more convenient for the patients than twice a day. And some of that recommendation was based on, a structural model that came from some of the original work. So I do think like that work was like extremely valuable. It's just, it's just when framing it in the context of a decision, I think it's really important to consider more than one model. I just wanted to highlight here a paper where they actually did that. So this was in Copenhagen. They actually had 5 different consultants try to make a prediction of aquifer vulnerability in Copenhagen. And they had like 5 wildly different predictions. And then this was really useful information to have. I think, like, I suspect if you're just developing like a PK model based on some PK data, my guess would be if you gave 3 modelers the same data, they would come up with something fairly similar. But for more complex mechanistic models, I really don't know. I mean, this is a type of thing, of course, it's really resource intensive to develop these models. And so we almost never look at this kind of thing, like how much do the predictions vary by model or vary by like what data is included. But I just mentioned it as a way, if we wanted to really invest in understanding this kind of uncertainty, this is like one approach you could take. The other thing I wanted to highlight, the example I presented, it was still a pretty simple model, right? There were maybe like just a handful of equations and parameters. But, with the more complex mechanistic models that we often use, it's the same issues can arise. It's just it's just a lot harder to put a presentation together, identify like, what the key issues are. And yeah, so finally, I just wanted, the hope, I think, is to have everybody kind of like work together, the modelers together with the stakeholders. Like a few years ago, I gave this presentation to the FDA, and the kind of call and the goal still is to kind of work with them in terms of developing methods and techniques for, how do we like validate models when we go to submit them. And like the summary is, again, when it's possible, I think a simple heuristic is a really great way to go, because 95% of the work is developing the mechanistic model. If you can come up with a simple heuristic too, that takes just a little bit of time and gives you a chance to benchmark. But in cases where that's not possible, using the credibility assessment and the pedigree table are additional tools you could use. So finally, I just wanted to think, one, I had some discussions with Andrea Saltelli about this. He had some really great papers, and especially one just in arXiv, just a commentary where I like learned about pedigree tables and things. I didn't even know about that like a few years ago. And then also at Novartis, I just wanted to thank all the colleagues I've worked with there. I mean, at Novartis, we have a few different modeling groups, and we have some that focus on the preclinical space and build more mechanistic models, and then others, like I'm in a group that's in more the clinical space. And so, but we have to work closely together. And so we work together on building this tool. And often, when it comes to, me trying to understand the results from what they've done and think about how will I apply it in the clinical setting, it's kind of working in this framework. It kind of helps me to think about the right questions to ask. Yeah, so that's everything I had. Thanks a lot, and I'm happy to take any questions.